Hey, so welcome back. So everybody see my post on Teams about the grade distribution of the midterm one. But before I actually goes into those details, right? So ask yourself, are you satisfied? So and let's see this quickly, okay? It looks like we still have some people need to actually rework on this. Okay, but I want to share with you about the distributions. All right, so this is actually the distribution of our class. The average is 63, I believe. Okay. So this is good or bad? Bad? Good? How many kids do we have in this section? 500, okay? 500 kids. Look around, how many do we have now? How many? 100 at the most, right? So just count, okay? So everybody know what the Gaussian distribution is or normal distribution? Okay, so typically the course was designed in a way that we always want to have a normal distribution for every single course, right? And the typical average the scientists expect to have is 60, right? The center location of that peak is 60. Okay. Look at this, okay? Look at the distribution. Okay, tell me, do you see a normal distribution or not? We don't. Okay, it looks like so-called a bimodal distribution, meaning actually you see a two population. Okay, we say we have 500 kids in these sections, right? How many of you get a grade 70 and above? Okay, so in that distribution, guess how many? Okay, so this is actually a breakdown of every single bin, going from 0 to 10, okay, all the way to 100. How many do we have for people that have score that's above 70? Around 250 people. Okay, so half of our class have a grade above 70, which is amazing. It's very difficult to achieve. Okay, so great job. Okay, happy for you guys. Okay. However, you know, everybody now get a sense why I say we have a bimodal distribution, because we have a group of people who already know how to handle the CHEM1312 already. The method you use so far works. Okay, all you need to do is actually keep doing the same thing until the end of the semester. Then you'll be able to get the grade that you want. Okay? Look at this. You see, the right three bins are the one. I hope those are the ones who actually follows my instructions. You do what I say. Okay? I'm pretty confident that if you really do everything I say, you should belong to the top three. Okay? But we do have a big tail, right? I always see that actually in all my lectures. It's always like that. There'll be a group of people who listen to me, who believe me, who follow my lead. You guys are taking care of yourself after midterm 1. Okay. But you can see we also still have another half of our students. Okay. They still struggles. Okay. That's the part I need every single of you who came to this lecture. Okay, do me a favor. If you know your friends, they are not actually doing the things I asked you guys to do, tell them to trust me. Okay, I am very available. I'm willing to devote my time to help your study, but you need to let me. There's actually at least half of students I will never actually reach them because they never show up. They never actually tell me that they need help. Okay, and that's only that much I can do. Okay, I record all my videos, right? I upload everything for you. I tell you, okay, watch my hangouts. I tell you how to prepare the exams. Okay. I think I do my part. But still have 200 something kids that I never actually have the access to them. Okay. They are your friends, most likely. Okay. So if you know people like that, ask them to really come to the lecture, do the things I ask you guys to do the same thing basically. Okay. Then they should be able to actually recover. Okay. And then for the grade wise, okay, average of 63 is not bad at all. Okay. But I believe people are actually sitting in this room right now. If you just look at the top three bins, right? The average is actually close to 80 something. It's crazy. Okay, so do you feel like you do things so differently compared to your Ken 1? I guess not, right? Because the amount of effort we can actually put in is that much. Okay, but do you see the power that if you know how to handle things in a logical way, okay, you can see the outcome with significant improvement. Yeah, I hope that's actually the feeling that you got after midterm 1. Okay, so I'm happy for you guys because you guys are the one who actually follow the lead from the beginning. Okay, so you actually have good hands now. Okay, you know how to actually do these things for the rest of the semester. Okay, so midterm 2 will be the one, okay, that typically the student do the poorest. Okay, you must heard these things all the time, right? So I want to share with you about my teaching last year. Okay, the average grade for my section specifically is the outliers. Okay, students actually do more or less the same as the midterm one, slightly lower, but not too much. Okay, and then the reason I can do that is because I feel like after midterm one, students trust me more. They start to actually understand what I mean by follow my lead, do the things in my own way is the easiest way to get the grade that you want. Okay, so I will say the same thing to you guys. Okay, just do what I say. Okay, make sure you actually can see the question as the way I see it, solve the question as the way I solve it. It makes your life actually a lot easier. All right, so that's actually a quick summary of the midterm one. Okay. What we are going to do after this, okay, I urge everybody in this room to do this, okay? You can see your midterm one now already, right? Download it now. Okay, download it with the correct answer displayed. Okay, you need those things for your final. Okay, when we hit the finals, you have several subjects going to have the exam time very close to each other. You don't have that much time to actually go through the materials, right? So the most efficient way is actually really go back and re-practice all the questions they have encountered and accumulated so far. Okay, this midterm one exam will close next week. So I urge everybody, if you have the access to it now, download it now. Okay, that's the safest way and the most responsible way for yourself to have a reference for your final. Okay? And the other things that we will do coming up very soon, I will post these things on Microsoft Teams as well. It's like there will be 2 points for so-called teamwork, right? So that's actually 2 points for your final grade. So it means a lot. Okay. The way we are going to give you those 2 points is by asking you to participate in the midterm survey. As long as you do the survey, you got 2 points. Okay. So I will create an assignment on Microsoft Teams. Okay. Make sure you actually do that. Okay. Yeah, once you do that, okay, next week I'm going to input all the people who actually did that. You got 2 points by doing the survey. Okay, very simple. Okay, if you don't do it, you may actually hate yourself at the end of the semester. Okay, so very important. Okay, yeah. So other than that, any other questions? Okay, if not, then we're going to finish chapter 13 today. Okay, and there's only one thing we're going to talk about today, which is extremely important for your midterm too. Okay, so on the board is actually the things we want to go through today. Okay. There's actually only one thing we want to actually calculate. That thing is called the pH. Okay, so I want to calculate the pH of a solution. Okay. And in chapter 13, there are 4 different types of solutions. Strong acid, strong base, weak acid, weak base. Okay, each different kind of solution has its own way to calculate the pH. And our job today is really just to get you familiar with how we do all the things quickly and correctly. All right? So everybody got this screenshot already? Or you can actually go back and rewatch the video. Okay, this is actually something that you want to actually memorize. Okay, Another thing that I've been talking to a few students yesterday and today. Okay. So if I ask you to memorize equations, memorize it. Okay. No discount. If I say memorize 3, then those 3 are the 3 you need to memorize it. Okay, because you are going to use it. All right, so first thing first, I want to start to think about the aqueous solution. Okay, think about a water solution. Okay, so when you have a cup of water, what do you actually have inside the cup? Hmm? Air? No, just water. Okay, but when I say water, okay, so this actually things that students never actually get a sense in the very beginning, right? When I draw these things, right, I say this actual beaker inside is actual water. So we know the chemical formula for water is H2O, right? That's its chemical formula. Okay. So 1 oxygen with 2 hydrogen attached to it. Okay. When you have water in a beaker, do you always have H2O? Yes. And only H2O? Okay. Tell me one more thing, okay? I want to actually say something that you heard all the time, but I guess you doesn't really actually understand it. What's the pH of water? What does the 7 means? 7 means neutral. Okay, so from a more atomic perspective, what does that 7 means? Okay, so we don't know, right? That's the things they want to actually talk about. What does pH stand for? Anyone know what pH stands for? Okay, that's actually the definition, scientific definition of pH. Okay, so it is negative log. Okay, that log means actually a base of 10. Okay, negative log of what? Concentration of H plus is proton. Okay, so proton concentration. Okay. Everybody get this? Proton concentration. Okay, so if you take the negative log of that, they give you a value of 7 for water. Okay? It means actually inside your water you have what? Not just H2O. You must also have protons. Okay? Where's the proton coming from? You only have water, right? You only have water, right? What does that mean? Okay, so when I say you have a water, okay, you are not just have water. You actually have water molecule and the dissociative form of water, which give you protons and hydroxide. Okay? Everybody understand what I just saying? Okay, so you need to actually have a clear distinction of water molecule, H2O, it is different from proton, which is H plus, and hydroxide, OH minus. Okay. This tells you that at any given temperature, okay, your water is going to dissociate. Okay, and once it dissociates, it produces proton and hydroxide at the same time. Okay, what's the concentration of lead, proton, and the hydroxide concentration? What's the concentration of lead? Let's go back to, do you know the pH of water? What's the pH of water? Yeah, everybody knows 7, right? So if you focus on this, if you take the 10, you can move the negative side to here. Okay, then you take the 10 to that power. Then this and that will cancel out. You end up with H plus equals to 10 to the -7 molarity. Okay, so inside your water, you not just have H2O molecule. More importantly, you have 10 to the -7 m protons. Okay, is that a lot or very little? Very little, right? 10 to the -7 is a very, very small numbers. That means inside your beakers, you do have tons of H2O molecules. Okay, but there's actually some of the water molecule that dissociate. Okay, and the concentration of the dissociation can produce 10 to the -7 m protons. Is that clear? Okay, that's actually a picture you have to have in your mind. Okay, it's not just water, it's actually water, proton, and hydroxide. Okay, what's the concentration of the hydroxide in water? 10 to the -7 is equal amount. Okay, so your water is still neutral. You have your Ki H plus, Ni OH minus. They are the same amount. The charges balance out as well. So you still have a neutral aqueous solution. Okay, so the reason I want to bring this out is because once I write this, I can write the equilibrium constant of this equation, right? The equilibrium constant will equals to H plus concentration times OH minus concentration. And we know it's 10 to the -7 on both, right? Therefore, we know the equilibrium constant for water is 10 to the -14, and then this actually is something that you need to memorize. For water, okay, the equilibrium constant for water dissociation is 10 to the -14. This is actually something that you must memorize. All right? Okay. So up to this point, we actually start to think about the water in different way now, right? It's not just water molecule, but inside aqueous solution, you can see that you actually have 3 different species. You have a bunch of H2O molecules, but you have some fraction exists as H plus, some fraction exists in the OH minus. Okay, and they are the same. Okay, and then if you count the concentration, and then you calculate your pH, okay, which you should remember that the pH means negative log of your proton concentration. They will give a value of 7. Okay, so those are the first things that you should really understand. Okay. This is actually why we actually write the things. Okay, KW, okay, equals to KA times KB equal 10 to the 14. Okay, we're going to talk about what KA means and KB means later on. Okay, but you should remember like KW is always equals to 10 to the negative 14 in aqueous solution. Okay, then mathematically, okay, every time you see this little p, lowercase p, okay, it means a mathematical operation. Okay, it means take negative log okay, of certain things. Okay, so later on we will learn a term called the pKa. Then it means negative log of Ka. Okay. Everybody fine with this definition? So what is POH? Is negative log of OH minus concentration. Okay, so you should actually have this sense now. Every time you see in the textbook or in your questions that you encounter, it says P certain things. What it really means actually, I take the negative log of less specific species. Okay, so I guess that's actually kind of changed many of the things that you feel like you know what pH means, right? But now we actually go into a very quantitative way, tells you how scientists define the term pH. Okay, it's all about the proton concentration. And we use how much proton a species can generate it, okay, to define its actually strong or weak acid. Okay, for the strong acid, okay, what is strong acid? That means actually throw the acid into the water, it dissociates 100%. Okay, so that's what the definition of strong acid. Okay, very easy and very straightforward, right? How about weak acid? Weak acid are the one that cannot dissociate 100%. Okay, so those are the very simple things that you should actually have in mind. Okay, and what we are going to do today is actually to tell you how do you calculate the pH of strong acid and weak acid. Okay, so this is the definition of pH. I hope by now everybody can understand that, right? Negative log of the proton concentration. Specifically, proton concentration at equilibrium. Okay, so on chapter 12, we'll talk a lot about this ice table, right? Yeah, so every time we calculate pH of a solution, it has to be at equilibrium. Okay, so this actually time I specific says proton concentration at equilibrium, but in the future, I will make that as a default and I don't write it anymore. Okay, but you need to know that every time when you're trying to calculate the pH, your system must at equilibrium. That means actually the value you should actually input has the value on that third row, right? At equilibrium row, okay? So how to actually figure out the proton concentration of strong acid or weak acid at equilibrium? Okay, that's the things we want to discuss now. Give me a strong acid that you know. H. Okay, how many strong acids do we have? Good. Which one is the strongest one? HI. We'll start with the HI. Okay, so HI is a strong acid, right? You solve it into water, what will it become? H plus plus I minus, all in aqueous solution, right? Okay, so let's do the ice table quickly. Let's say Initial, I have 0.7 N. If I solve HI into my water, okay, it ends up with a HI solution with 0.7 molarity. Okay, can I calculate my pH use that 0.7 directly? You cannot, right? Because it's actually at the initial state, right? The number you can actually use to calculate your pH has to be at equilibrium, right? Therefore, you need to actually go from the I all the way to the E first, right? But we know HI is a strong acid. Okay, that means it's going to dissociate 100%, right? That means here you're going to put negative 0.7. Here you're going to put positive 0.7. Here will be positive 0.7, right? So that at equilibrium, do you still have HI? You don't. You don't have HI anymore. Okay, what do you have remains? It's 0.7 N of H plus, right? And then 0.7 M of I minus. Okay? Any question for this step? You good? Okay. So now you have the concentration of H plus at equilibrium, right? Can you calculate pH now? Yes. Okay. So the pH will be what? Negative log of 0.7, which will give you a value of. Where's your calculator? Bring your calculator out. Okay. What's the pH? Zero 0.15. Everybody get the same value? Okay. So this is actually the first thing we want to learn today. Okay, how to calculate pH of a strong acid. Okay, so we went through this ICE, right? So we can actually know what's the proton equilibrium, proton concentration equilibrium, right? Then we actually calculate our pH. Do you notice that the proton concentration is actually the same as your strong acid concentration from the beginning, right? Our HI concentration was 0.7 from the beginning. And your H plus concentration is also 0.7 at the end at equilibrium, right? The reason that is the case is simply because it is a strong acid, it dissociates 100%. Therefore, your initial concentration and proton concentration, they are equivalent. Okay? This is a very important concept because later on in our lectures, okay, where I ask everybody, don't go through the ICE table because it takes time. You need a time for other calculation for your midterm too. Okay, so the things I want to summarize for you is that, remember this. Okay, this will be the take-home message that we want to have. Okay, if today I give you a strong acid, okay, and I specify the concentration of that strong acid, then you should know that the proton concentration at equilibrium will equal to that strong acid concentration. Is that clear? Okay, and then the reason for that is because for the strong acid, you will always dissociate 100%. Okay, so let's actually the conclusion. Okay, therefore you know the pH of a strong acid will simply equals negative log of your proton concentration equilibrium, but when you do your calculation, you can just use the strong acid concentration directly. Okay, So have like this in mind. That means actually, if you recognize a solution is a strong acid, to calculate the pH, you just technically log of less strong acid concentration. You'll get the answer correctly. Okay, so instead of going through all the things we went through, you can just use the equation to get the answer, I don't know, within 10 seconds. All right? So let's actually the first things that we went through here. This is actually why I say this, right? If you have a strong acid, okay, then you know the proton concentration at equilibrium will be the acid concentration from the beginning. Okay? Then we go to a more interesting situation, the weak acid. Okay. Let's say I have a weak acid, which I always use HA to represent my acid. Okay. So let's say HA is actually a weak acid. For a weak acid, you're going to produce H plus and then A minus. Okay. How do you define the equilibrium constant of a weak acid? It will equals to proton concentration times your conjugate base concentration divided by your weak acid concentration, right? Okay, I want to actually go slow here so everybody can follow me. Give me a weak acid. Acetic acid, CH3COOH. Okay. So if you store the CH3COOH into a water, what are the molecules existing inside your water solution? CH3COOH and H plus and CH3COO minus, right? Because it dissociates, okay, but not dissociate 100%. Okay, of course, you still have a bunch of water molecule inside the container. Okay, and then the water will also produce some small amount of H plus and OH minus. Okay, but every time we say we have a weak acid, okay, the protons that got generated from your weak acid, okay, typically it's actually much higher than the proton generated by the H2O. Okay, so you only need to actually consider the proton generated by the weak acid. Okay. So when you have a weak acid, then you're going to, for every single weak acid, you can actually always check the table. Okay, they have this so-called Ka table. The K again is your equilibrium constant. The lowercase a represent it is the equilibrium constant for acid. Okay, so later on we will see another one called Ke. Okay, that's actually the equilibrium constant for a base, actually weak base. Okay, so don't let those subscript confuse you. Okay, focus on the big K. That big K is just telling you that it is just an equilibrium constant, right? Which indicates the ratio between your product over reactant. Okay, it's basically exactly the same thing like what we learned in chapter 12. All right? Okay, so let's do the same analysis. Okay, let's make it simpler. Okay, let's say I have 1N to start with. Okay. The question will be like this, okay? I have 1N, let's say acetic acid, CH3COOH. Okay. So I want to know the pH of the solution. So this will be a very standard type of question you're going to encounter in chapter 13. Okay, so how do you actually handle that? Okay. Because the concentration given is your acetic acid, right? Therefore, you know that is not the same as the proton concentration at equilibrium. Okay, That means actually you need to put it right here, at the initial state. Okay? Then what? We know they cannot dissociate 100%. Right? Therefore, you can just do the things we do for the strong acid. So what you handle here is actually, let's say, I have X percentage got dissociated. Okay. And then once I do that, I know I'm going to produce X for my H plus and A minus. Therefore, I know once I reach equilibrium, it will be 1 minus X, X, and X. Right? So these are exactly the same how we do it in chapter 12. Okay, everything is actually the same. Okay. Then we know how all these terms is associated with your equilibrium constant Ka, right? Because I can write my Ka now is going to equals to photon concentration, which is X, A minus concentration is X, right? And then your HA is simply 1 minus X. Okay, so this will be X squared, 1 minus X. All right. So from this equation, you know, if you solve for your X, then you take next log of the X, which is your proton concentration, then you get your pH, right? So that's what we're going to do. Okay. So you want to actually solve for your X. One thing that's interesting for the weak acid is that your Ka is typically small. Okay. So here we're going to apply a very important concept called the small x approximation. Okay. Okay. So what it means is that when we say small, okay, small means your x is smaller than 10 to the negative 3. Okay. So what happens if your x is actually so small? Okay, the things that you are going to see is that I want to focus on this term. Specifically, the denominator. What happens if your x is very small? The 1 minus x will be very, very close to, right? So 1 minus x will be very, very close to 1. And they will actually make your life a lot easier because here, you know, the Ka equals to x squared 1 minus x, right? If x is actually so small, your denominator becomes just 1, right? Therefore, you know, your x can simply be equals to your Ka times 1. Okay? And then here we know your x is actually represent the proton concentration at equilibrium, right? What is the 1? What is the 1? The 1 is actually your initial weak acid concentration. Okay? So this is the equation I want to actually memorize. If today you have a weak acid, when your Ka is smaller than 10 to the negative 3, then your proton concentration at equilibrium was simply equals to Ka times your initial weak acid concentration. Okay? Once you have that, you take the negative log of that equilibrium proton concentration, you get the pH of the weak acid solution. All right? Everybody follow these things all right? Okay. This is very important because you realize that this will save you tons of time. Okay. The reason I want to go very slow on this is because I want you to see how I actually came to that specific equation. Okay. And that equation is applicable for any weak acid. Okay. So instead of going through that ice table, all you really need to do is actually just recognize what solution that you have. If a weak acid whose Ka is smaller than 10 to the negative 3, then the proton concentration at equilibrium was simply equals to the square root of Ka times your initial weak acid concentration. Okay, so you don't need to actually do the ice table anymore, which saves you tons of time. That's the things that you will need for your midterm too. Okay, everybody okay? Follow with this? Good. Okay, so once you can do this, then calculate pH will simply just take negative log of that. Okay, so with that, we can come back to these things again. See, for weak acid, which we want to actually apply the small x approximation, okay, then you can calculate your proton concentration using this square root of weak acid concentration times your Ka. Okay, so these are the two very, very important and useful equations for the acid. Yes. Yes. So Ka has to be smaller than 10 to the negative 3. Of course. So what happens if that's the case that you have? It's good questions. So easy. Okay. So it's actually great questions, right? So what happens if I cannot use small x approximation, right? So let us actually the time that you actually really solve this quadratic equation. Okay, so what it means is that here, so here, if you cannot use small x approximation, then you really need to actually expand or multiply 1 over x on both sides. Okay, and then Ka is actually you're going to get a value of Ka. Okay, but let's actually make it become a quadratic equation. Then use the quadratic equation formula, get your x. Okay, so great questions. Okay, but that will only be needed when your Ka is smaller than 10 to the larger than 10 to the negative 3. All right. Any other questions? Okay, if not, then we can go to this. We've been talking about the acid so far, right? But what if today you have is actually a base? Okay, so the way you handle acid and base, they're actually basically the same, but you actually replace your H plus with OH minus. You replace your Ka with Kb. Okay, but you can see that if you're strong base, the OH minus concentration will be your initial base, strong base concentration. It's exactly the same as the strong acid, right? You just replace the acid with base. Okay. Similarly, for your weak base, you can calculate the hydroxide concentration at equilibrium using the square root of weak base concentration times Kb. Okay, so don't mess up Ka and Kb. It's base, Kb, acid, Ka. Okay, so it's very systematic way to actually memorize how you can calculate the proton concentration or hydroxide concentration at equilibrium. Okay, so this will save you a lot of time. Okay, so once you get this, then you can take the negative log of that. Then they'll give you the pOH, right? To calculate the pH, you need to do one more step. It's that the pH plus pOH in aqueous solution is always equals to 14. Okay, so that's another thing that you need to actually memorize so that you know how to convert the pH from your pOH. Okay, so that's actually all the equations for chapter 13. I hope it's actually easy enough for everybody to memorize right now. All right. Now it's actually want to do 3 more questions, and that's it for today. Okay, let's read these questions. Calculate the pH of 0.1 m solution of ascorbic acid for which the Ka value is 1 times 10 to the negative 5. Okay, what's the keyword here? pH. Okay, so every time you see pH, you go back to the things we just talked about. Okay. So every time you see pH, the first question you need to ask yourself is, what kind of solution that I have? Okay, strong acid, strong base, weak acid, weak base. Okay, later on we'll learn another one called buffer. Okay, but for today's lecture, we'll only talk about the 4, right? Strong acid, strong base, weak acid, weak base, right? What kind of solution do you have? Weak acid. Okay, how do you know it's weak acid? It's not a big 7 first, right? Second, there's actually another clue here. You have the Ka. Okay, for strong acid, there's no Ka because it's 100%. They cannot define the Ka. Okay, so every time you see the Ka, you should also know that this most likely is something weak. Okay, most likely it's actually acid. And here it's actually very clear because you say you have a ascorbic acid, right? Do you need to know the formula of ascorbic acid? You don't, right? So every time when I teach this, I want you guys to don't be scared by the name. Okay, all you need to do is actually, okay, it's acid, then I just write HA. Okay, and I know it's weak. Okay. So the Q is, I want to know the pH of a weak acid solution. Okay. Weak acid solution, then you should know that since acid, right? Therefore, you know the things you are looking for is the proton concentration at equilibrium. And that one can be calculated using the square root of Ka times your weak acid concentration, the beginning, right? So I'm just doing the same thing that we just went through. Okay, so that will be actually your plan, right? Then you look at your data. The data that you know the weak acid concentration is 0.1 m, right? Ka equals to 1 times 10 to the negative 5. 1 times 10 to the negative 5, that means small x approximation is good, right? Therefore, you know this equation is good. Okay, therefore you can actually solve this. You know your proton concentration at equilibrium will equals to the square root of Ka 1 times 10 to the negative 5 times your initial concentration 0.1. Okay, that give you a value of, what's the value you're going to get? Okay, I want to keep reminding everybody, okay, midterm 2 and midterm 3. Actually, that's all, right? 2 and 3, and then you'll be your final. Okay, midterm 2 specifically. Okay, you really really need to be an expert of your calculator. Okay, conceptual-wise, I'm very confident that I can let you understand how to do the calculation. Okay, but getting the correct number is your thing. Okay, even if you know how to calculate it, you may not actually get the correct number if you don't know how to operate your calculator perfectly. Okay, so do practice a lot with your calculator. All right. Okay, so now you know the proton concentration is 10 to the negative 3 m. Therefore, the pH will simply equal to negative log of 10 to the negative 3. They will give a value of 3. Okay, for this weak acid solution. Okay. Any questions so far? Very simple, right? Yeah. Can you believe this type of question actually makes students feel so confused? Hard to imagine at this point, right? Simply because we introduce you a way that's actually very simple. Okay, so that you don't overthink it. Okay. And then I also want you to think about this. How long does it take for me to solve this problem? 20 seconds, right? Think about if you start to write your ice table. Think about you start to write your minus x plus x. Think about it, start to write out the Ka equals to x squared over 1 minus x. And then you say, okay, small x approximation. How long will it take? It may not take very long, right? But it still takes a lot of time. Okay, that's why I say to you, I want you to see how I come to that final simple equation. Okay, but once you know how it works, adapt it. Okay, then you know all the things you want to make sure is that the Ka is small enough that you can use small x approximation, right? Then you don't need to do the ice table. What if today the Ka is actually not that small? Then you need to actually go back to your ice table, redo everything, okay, in the old way, okay? But from my all the questions I've observed so far, okay, majority, 95% above, your K is actually smaller than 10 to the negative 3. Okay, so knowing this will actually speed you up quite a bit. Okay, so don't go back and use the ice table unless your Ka is really big. All right? Let's do 2 more. Okay, calculate the pH of 0.6 m solution of ethylene amine. Okay, they give you the chemical formula and give you the Kb. Okay, what's the keyword? pH, right? Okay, so then after that is, what kind of solution do we have? Weak base. Okay, so ethylene amine, which is this guy, has a Kb of that value. Okay, so you know, weak base. All right, so Q is actually I want to calculate pH of weak base, right? Typically, I use BOH to represent my base. Okay. Data that I have is that the weak base concentration is 0.6 m. The Kb of the base is 5.6 times 10 to the negative 4. Small x approximation, okay. Right? Then the plane, since it's base, right? So we start from the OH minus at equilibrium. Going to equals to square root of, anyone remember the equation now? Kb times the weak base concentration, right? Therefore, we know it's going to equals to square root of 5.6 times 10 to the negative 4 times 0.6. And then we are going to get a value of 0.018. Okay, then you can write your POH, which equals to negative log 0.018. That's going to give you a value of 1.74. Okay, make sure you actually get 1.74. Then your pH will simply equals to 14 minus your POH, which is 14 minus 1.74. That can give you a value of 12.26. Okay, very simple. All right, so it's pretty much the same. Okay, so the only difference is actually we go from acid to base. Okay, therefore we start to calculate the OH minus concentration at equilibrium. All right, so that's actually how you solve these questions. Next. This is actually one of the most confusing questions of this chapter. Okay, so let's read this. The pH of 0.269 methyl ammonium chloride C2H5NH3Cl. The Kb of ethylene amine is 4.3 times 10 to the negative 4. Okay, keyword, I guess no one has problem, right? pH, right? Okay, so we know the keyword is pH. Then the next question is actually what kind of solution do I have? Okay, so here I want you to become more careful. Okay, think a little bit. Tell me what kind of solution do we have? See, this is actually the time let students get confused. Okay, let's start from the simple question first. Strong or weak? Weak, good, because you see the Kb, right? Now, acid or base? What is actually the solution that you have specifically in these questions? What's the solution that you want to calculate the pH? It's this guy, right? Everybody see, that's actually the one you want to calculate, right? Is methyl ammonium chloride. That's the solution that you have. Okay. Then you see the Kb, right? What's the Kb? The Kb of what? Ethylamine. So it should be actually, there's actually one letters here. I have that. Okay, so the solution that you have is ethyl ammonium chloride. Okay, but the Kb is for ethylamine. Okay, first thing first. Are these two the same species? They are not. Okay, so science is very rigorous. Okay, if they look different, they are different. Okay, don't pretend they are the same. They are different. Everybody agree? Okay, so now look at this. It gives you the Kb of a substance called ethylamine, right? That means your ethylamine is a weak base. So there's no doubt. Okay, if I give a Kb of a certain substance, this substance has to be a weak base. Okay, but is this substance the substance you need for solving the questions? No. Okay, then why do they give you the Kb of the substance? So this is actually the part, okay, we need to have some extra knowledge. Okay, so we know these are two different substances. But, Okay, this will shows up over and over again. I want you to see this is 100% clear. This guy, okay, and leg guy. First, compare the two. What's the differences? So the ethyl ammonium chloride compared to your ethylamine, you have extra HCl, right? You got H and Cl, right? So one thing that you should know, this guy is actually a salt. Okay, every time you see a species attached with the 7A elements, for example, bromide, fluoride, iodide, okay? The things that you should ring a bell is that this is a salt, okay? And then it will dissociate. Once it dissociates, then you know the 7A always carries -1 charge, right? Everybody understand this? Okay. What's remain will be your C2H5 NH3 plus. Okay? Everybody can recognize this? It's a very important step. Okay. Now, once you can actually recognize this, I want to compare to these two. What's the difference between the two? Extra H and plus is H plus, right? It's the amine with H plus. Okay. Why do I want to emphasize this? It's because remember we talked about this thing called the conjugated acid base pair. Okay. C2H5NH3 plus is the conjugated acid of Lewis base. Everybody see this now? It is a conjugated acid. Make it a weak acid. All right, so you know the species that you have is not a base. It is a weak acid. Okay? So how do you calculate the proton concentration at equilibrium of weak acid? It will be square root of Ka times weak acid concentration, right? So if I use Ha to represent my weak acid, I should do this, right? So that's actually exactly the things we do in the first questions, right? Weak acid, the proton concentration at equilibrium equals to square root of Ka times your weak acid concentration. Okay, so that's the things I want to do. Okay. But do I have Ka? I don't. Okay, so let's actually another very important equations that we will need to actually memorize is that okay, the Kw is actually 10 to the -14, right? So here, this example tells you what? The Ka and Kb of a conjugated acid-base pair, they can be calculated through that equation. Okay? So since this question doesn't give you Ka, okay, instead it gives you Kb, but you can use that relationship to back calculate your Ka. Okay. Then you can actually put it into this equation to calculate your proton concentration at equilibrium. All right. So let's calculate Ka first. So Ka can be calculated using your Kw over your Kb, which is 10 to the -14 divided by 4.3 times 10 to the -4 they will give you a value of 2.3 times 10 to the negative 11. Okay, therefore you know you can still use your small x approximation, right? Means you can really calculate your proton concentration use this equation. Okay. So you know your proton concentration at equilibrium will equals to Ka now is 2.3 times 10 to the negative 11. Acid concentration 0.269. Okay, then you're going to get a value of 2.49 times 10 to the negative 6. Therefore, the pH will equals to negative log of your proton concentration, 2.49 times 10 to the negative 6, which will give you a value of 5.6. Okay, any questions? So this question, okay, this type of questions is the one that students make the most mistake. Okay. The reason that it's actually confusing is because students is not very fair. Okay, they treat the acyl ammonium chloride the same as the acyl ammonium. Okay, that's not the things that you should do. Okay, so every time you see a question like this, when you start to recognize that the species that you will ask to calculate your pH is not the same molecule that was provided with the Ka or Kb, then you know that species is the conjugated acid or conjugated base of whatever species provided with Ka and Kb. Okay, so use this as an example, right? It gives you the Kb, which means that the species that provide is a weak base. But that is not the species was given to calculate the pH, right? So you should actually ring a bell that you should know, I don't have a weak base. I actually have a weak acid. Okay, so having that concept, that simple concept, will actually put you in the correct pathway. Because you know, I have a weak acid, therefore I should calculate the proton concentration, right? But under the case, you know, you will need to have the Ka. Therefore, it will naturally force you to back calculate Ka using the Ka times Kb equals Kw. Okay, so these are the things that you should really pay attention to. Okay, if you can recognize that, you should be able to do all the homework correctly. Okay, so I will stop here today, but make sure you go back and rewatch all the things. Thank you.